So finally, let us see on how we can be able to analyze this case of the projectile motion, having gone through actually ground back to ground case, top angle ground case, and also top horizontally released ground case of the projectile motion. Now make sure that you have understood all these cases of the projectile motion as you are to go for this. So keep that in mind. Let's say we have the object. Let's say we have a building which is giving us this. And say the object. Now let's say the object has been, let's say, released in this case. Let me just have to draw it in this way. Let's say the object has been released in this case. Now, say this is the horizontal axis, which is x-axis, and say this is this is y-axis. Of course, this is y-axis, this is the x-axis. Now, which means the object has been released, from the top below the horizontal x-axis in that case. Let's say the angle in which the object has been released with, it is given as this one as the angle theta. And let's say the object has been released with, say, initial speed given as, let's say, v. Let's say the building is of height given as, let's say, h. Now, what is the time takes for the object to reach at the ground level? What is the horizontal distance and for the object to reach at the ground level? Actually, for the object to move along x-axis to reach where the object is going to strike the ground, and some sort of. So now, principle remains the same. Analysis will be independently done. Now, this case of the projectile motion is said to be a top below horizontally released ground case, where the object is released actually from the top, but below the horizontal x-axis, actually below the horizontal axis, which is below the x-axis. So take note of that. So that's the case of this projectile motion, and we should have to analyze it finally. Now let's see start. Now, what is initial velocity along x-axis? That will be obtained upon resolving this into components. That will be given as v cos theta. And on the same note, which means the final velocity, which is v of x, the velocity of the object as it is going to strike the ground, will be given as v cos theta as well. Since along x-axis, object moves at a constant speed, from the fact that acceleration due to gravity is given as well. You can remember this. Now, what is the horizontal distance? The distance the object has to move along x-axis from the point of release to where the object is going to strike the ground. This is the horizontal distance. Now that one will be given as, should be horizontal distance. Horizontal distance, we'll have it as v cos theta times t rho. T rho is the term for the whole entire journey. That's the term for the whole entire journey. That is t rho. So the time it takes for the object to move from here up to this point is said to be the t rho times the distance, or half the horizontal distance. So that's the analysis along x-axis. So keep in mind that as the object is going to strike the ground, it will have the component of the speed along x-axis, that is v of x. Now, you start to understand it in this way. That's the, of course this is the horizontal distance, by the way. Anyway, take note of that. So now let's see on how we can be able to analyze the motion along y-axis. So principle remains the same. Vi actually y will be given as now v sin theta. Now only that this velocity will be given as negative because it is pointing downwards. So have it as negative v sin theta. That's the velocity along y-axis. And the acceleration due to the gravity is given as the negative 9.81 meters actually per second square. So how can we have the final velocity in which the object is going to strike the ground with along along y-axis, which is given as this? That is Vfy. So we'll have that and using the displacement for actually using the acceleration formula. That is Vfy is equal to negative g d dot plus, now have it as negative, which is this, so which means we'll have it as, so which means we'll have it as negative, v sin theta. So that's what will happen there. So we'll be able to have the final velocity as the object is going to strike the ground using that formula. Likewise, the magnitude of the landing will be given as this. So where we'll have the magnitude of this, these two components, and the direction will be given as this angle. You'll be able to have that and in that way. Of course, this angle won't be equal to this angle because this case of the projectile motion is not symmetric in nature. So take note of that. And how can we be able to have the height in which the object has been released from? So the height will be calculated using the displacement formulas. And in the sense that we'll have it as, so the height will be given as, now should be, height will be given as, initial velocity along actual y-axis, that is negative, sin theta, negative v sin theta, negative v sin theta, and the minus half, now should be times d dot rather, minus half g d dot square. So this is how the height of the building will be calculated, or whichever the height. And you can see that they will be given as negative because the displacement from here up to this point will be given as the height of the building, so we'll have it as the negative. Or else we have it as the displacement is equal to v, which is the final velocity along y, that is v of x, plus vfy, that is actually initial velocity along x-axis, that is, should be along y-axis, that is v sin theta, divided by 2 times time, which is d dot. So you'll be able to have that and up to, which means likewise, if you have the height of the building, you can be able to have the d dot using this formula as well. That is, or else you can also use this formula to have the dot time if we have the final velocity along y-axis, initial velocity along x-axis, and you have the height, you can be able to have the d dot in that way. So that's how you have to understand about the analysis of this kind of the projectile motion. Thank you.